Once we can identify how many significant figures are in a number, we can do calculations with those numbers. After we do our calculations, we will need to round. For the purposes of this class, we will be looking at whether the first number that gets dropped off is less than 5 or 5 or greater. If the first digit we are dropping is less than 5, we will round down. That means the last digit that we want to keep remains as is. For example, if we are rounding 7.94 to the 10th place, we are keeping the 7.9 and losing the 4. But before we lose the 4, it tells us whether to round up or down. In this case, since it is less than 5, we round down, and the 9 stays as is, giving us 7.9 for our answer. If the first digit we are dropping is 5 or more, we round up. That means the last digit that we want to keep will go up by 1. For example, if we round 7.95 to the 10th place, we are keeping the 7.9 and losing the 5. But before we lose the 5, it tells us whether to round up or down. In this case, since it is 5 or greater, we round up. The 9 gets rounded up to 10, so we keep the 0 from that in our 10th place and add a 1 to the 7, giving us 8.0 for our answer. There are two rules for calculations with significant figures, an addition and subtraction rule and a multiplication and division rule. The first step in any of our operations is to determine whether our numbers are exact or inexact. Exact values can be considered to have an infinite number of significant figures, so they do not affect the number of significant figures in our answer. For example, if I'm using the conversion 1 liter equals 1,000 milliliters, I can think of that 1,000 as 1,000.00000, etc. My second step when I'm doing an addition or subtraction problem is to figure out how many digits after the decimal each of my starting numbers has. My third step when I'm doing an addition or subtraction is to round my answer to the same number of digits after the decimal as whichever number has the fewest decimal places. For example, if I'm adding 9.572 and 82.76, I identify the first number as having 3 digits after the decimal, and the second number as having 2 digits after the decimal. Since 2 is less than 3, my answer will also have 2 digits after the decimal. Before I round, I do the full calculation with all of the digits and come out with 92.332. I identify which digits I am keeping and which digits will fall off. Since I need to round to 2 digits after the decimal, I am keeping the 92.33 and the 2 falls off. But before it falls off, it tells me whether to round up or down. Since it is less than 5, I round down. The 3 stays as is, and my final answer is 92.33. One thing that I have seen students do is to line up the numbers with the decimal points all in a column, like shown on the slide. Then you can draw a vertical dashed line after the number with the fewest digits after the decimal. In this case, it would go after the 82.76 and would end up cutting off the 2 in the top number and the 2 in the bottom number. This is a great way to remember to round based on digits after the decimal, but don't forget to look at that next digit that's being dropped off to tell whether to round up or down. What is 10.52 minus 8.955 using proper significant figures and rounding? Is it A, 1.57, B, 1.565, C, 1.6, or D, 1.56? The correct answer is A, 1.57. Our first number has 2 digits after the decimal, and our second number has 3 digits after the decimal, so we keep 2 digits after the decimal in our answer. Notice all 4 answer choices are variations on the same value with different numbers of digits. The answer is A and not D, because the 5 after the 6 in our unrounded answer tells us to round up. For multiplication and division, My first step is the same, ignore exact values. My second step is different. Instead of looking for digits after the decimal, I'm looking for how many total significant figures are in each of my starting numbers. In step 3, I round my answer to the same number of significant figures as the starting number that has the fewest significant figures. For example, when I'm multiplying 4.38 by 695.1, first I do the math, and my calculator gives me something like 3044.538. I identify how many significant figures are in each of my starting numbers. The first one has 3, and the second one has 4. Since 3 is less than 4, I keep 3 significant figures in my final answer. This is going to be a little tricky because I have to round to a digit on the left side of my decimal point. Remember, we have to keep the same magnitude of our answer. So 3044.538, rounded to 3 significant figures, is not 304, but is actually 3040. However, if we write it as 3040, the significant figures are ambiguous. And if we write it with a decimal point after the 0, it conveys 4 significant figures when we can really only keep 3. Therefore, the only way we can write this number with proper significant figures is using scientific notation. Writing it as 3.04 times 10 to the third gives the correct magnitude of the number and the correct number of significant figures. What is 607.90 divided by 9,176.74 using proper significant figures and rounding? Is it A, 0.0662436, B, 0.0662, C, 0.066244, or D, 0.06624? The correct answer is C, 0.06624. Our first number has 5 significant figures, and our second number has 6, so we keep 5 significant figures in our answer. Notice all 4 answers are variations on the same value with different significant figures. The zeros on the left are not significant, so the 6 is our first significant digit. We keep the 0.06623, and the last 6 falls off, but before it does, it tells us to round our last digit up to a 4. When we have multiple data points or types in our calculations, it is important to know how the level of precision of each of our data affects the level of precision of our overall answer. Here's an illustration of why this is important. In the 2016 Summer Olympics, as happens frequently, there was a 3-way tie for second place. You may be wondering, don't we have the technology by now to measure times more precisely than that? In fact, we can measure times very precisely, to the millionth of a second. However, when finding the fastest swimmer, what we really want to know is speed. The calculation for speed involves both time and distance. Although we can measure time very precisely, the way that the swimming pools are manufactured means that we are less sure about distance. There is a tolerance of about 3 centimeters in each lane. The low precision of the distance measurement leads to a low precision in calculating speed, so it is not possible to tell who really was the fastest. It could be the one who took slightly less time, also has slightly shorter lane. In the lab, we also need to be careful to do our calculations with the proper significant figure rules so that we can find the true precision of our results.